The next heap operation we're going to talk about is extracting the maximum element. If we wanted to get rid of the max, well, we'd chop it off here and then ruin the entire tree maybe? Because we would then be missing our root and we would need to find something in this entire tree to fill that spot, which looks like an issue. What we're going to do to extract the maximum element is, if we do not want to break our heap structure, the only element we are allowed to remove is the last element. The last element in the array is the only thing we can remove and not break the heap structure. So, to get around that, why don't we swap 11 up to the top and put 48 down here, and then cut it off of the tree? That seems like a decent solution, because now, after having performed this swap, the remaining tree still has the heap structure and we have not broken anything. Except I have told a blatant lie, which is that we have broken it horribly up here at the top, right? We have suddenly caused that a element that was at the bottom of the tree, which is presumably much less than the root originally, is now at the top. So we need to fix this. We are going to fix this by swapping 11 back down until we stop having broken anything. So let's look at the elements that seem convenient to swap with. I can swap with my left child or my right child. Well, both of those are greater than 11, so they both should rightfully be above it in the tree. And if I want to guarantee I don't need to do multiple fixes, I'm going to choose to swap 11 with the larger of the two. Now, because 42 is the largest of this trio of numbers, we guarantee that we do not need to perform any more fixes. Now we check, is 11 okay? Nope, because both of its children are still greater than it. So we're going to swap 11 with the largest of its children, which is 39. Then we check, have we broken the heap structure? Yes, we have, because both of its children, 34 and 31, are greater than it. So we swap. And then we put 34 in this location and 11 there. And now we check, have we broken the heap structure? Well, this node is cut off, so it no longer exists. So our heap structure is now maintained. And it looks like in this example, why didn't you just move 11 up? Programmatically, that involves some heuristic checks to discover where would the node likely go, and that is more sophisticated than we need to be. So this is going to be our algorithm. It will work every time, and its runtime will be sufficiently good for us. Looking at our code for the extract max, I'm first going to comment that I have a typo in this code. So here, we should also have a call just after that line 5, we should have a call to a of size is equal to a1. This is the line where we swap the root of the tree, with the last node. That was not included in the original code, so make sure you update your code to reflect that. So we need this one fix, and then we have, after we swap it around, we're going to remove it from the tree. We do that by just reducing the size of the tree. That will still be stored somewhere in memory, but as far as the tree is concerned, it does not know that that exists anymore. We then Max-Heapify, whatever that does, it magically fixes it for us, and then we return the max key. It's a beautiful function, right? Maybe we probably want to see how Max-Heapify works, but it looks much nicer this way, doesn't it? So let's see what Max-Heapify does, because everything here takes constant time, constant time, constant time, constant time. Looks like we have a glorious function, right? Not so nice, because we need to look at this Max-Heapify function. Here's Max-Heapify. It looks scarier than it is, because there's lots of things we need to be careful of in terms of moving variables around and not accidentally creating too much extra memory. You could implement this recursively. I believe that you typically do this in your software series. Here we are implementing this using a repeat until loop. Both are equivalent, and you can execute it however you want. We're going to begin by finding the left element and the right element. Once we found those, we need to find the maximum between our current element we are looking at, its left child, and its right child. All of this code here is doing that. So that is all we need to do with all of that code. Let's try and see what it does. We start by saying that the largest element is the one in the center. So let's draw this. This is J, this is L, and this is R. We start by assigning this one to be the largest, the one at the parent. We then check, is the one on the left in the array? as in, is there a child over here to even compare to? And is that child greater than the element I'm looking at? Largest is initialized to be j. If so, L is now the largest, so we update largest. We then check, does it have a right child? And is that right child greater than the largest we've found so far? So we've compared these two. We then compare whatever the larger two of those was to R. And then if that's larger, we set largest to be R. So it's just finding the maximum between those three elements. We then swap the largest with the parent. And if we don't need to swap it, we then check, did we change anything in that if statement? We check the largest between L, R, and J. If the largest of those was the original, we didn't perform any swap and our heap structure is now maintained, so we are done. So if J is equal to largest, we would go into this loop and we'd flag that we are done. If J wasn't equal to largest, that means we needed to swap things around and we need to keep trying to update this. We then descend the tree to either L or R accordingly to then keep going down the tree. One very reasonable way to analyze this function is to scroll back up to our picture, or even just think about the code there, and say what is the worst that happens. The worst that happens is that I need to descend the whole tree, and therefore this is bounded by log of n. So you might be able to say, just by a heuristic guess, this algorithm should definitely be in theta of log of n. That's all well and good. That is a very valid approach. Let us remember what our definitions were. We started with size, which is n. This is n. And we start with j is equal to 1. And then what are we possibly doing? We're either updating it to be L or updating it to be R in the worst case. So we're either doing j is equal to 2j or j is equal to 2j plus 1. That's what we're doing. So to be absolutely pessimistic, let's assume we're increasing j by as little as possible. That would take the longest to terminate. So in the worst case, we're doing j equals 2j at every single step. So j, if we're creating an iteration table, iteration, and j starts at 1. We then multiply by 2, and then multiply by 2. And after gamma iterations, we will have 2 to the gamma. We can then solve that for the largest value j could obtain, which is necessarily the size of the heap. So gamma is equal to log base 2 of n. So again, with a more rigorous analysis, we also can arrive at the fact that this is in theta of log of n. And this is the runtime we will typically use. Notice that log of n is the number of elements in the heap. We may actually be storing, as we've seen in this code up here, fewer elements than the array's size, so we'll need to keep that in mind. So if this code here takes log of n time, then max heap insert is in theta of log of n. We'll ignore the expected case runtime and just assume that it to be log of n for our purposes. That's a bit beyond what we want to do when analyzing this data structure. The last thing I'll comment on is that this code was a bit messy. You could write this a bit nicer with a mathematical concept called the argmax. Argmax of elements doesn't just return the maximum, it returns the maximum index for us. So rather than this ugly code block here, what you could do is say let the largest element equal the argmax over certain elements of A. This simplifies it by making someone else deal with it and writing it in a more mathematical way. This is useful in pseudocode though, because it makes it more readable. This function, to somebody that understands the mathematics being written down, is much easier to interpret than this more implementation-minded writing of the code. And when writing pseudocode, it is always good practice to make it as abstract as possible and therefore as language independent as possible so that people can implement it in whatever language they are using the language constructs that exist within that language.